Okay, let's charge into another example. We're getting close to the end of chapter 7, actually. We're going to do another confidence interval around a mean. Remember that there are two formulas for doing this formula and this formula. In fact, let's go ahead and add the 7.2s to them. We have the 7.2 and the 7.2. If you know the population standard deviation, then you can use this formula, and you can use the z-table to get your critical value. That's if you know the population standard deviation. If you don't know the population standard deviation, you use this formula, and you use the t-table and degrees of freedom, which remember is n minus 1, and you use that table to get your critical value. Now, one of the nice things that I really want to stress with this is what I'm kind of teaching you is how science works and how the scientific method works. Because people think that science proves stuff, but that's actually not the way it works. What science does is you create a hypothesis and you test it, and like with a confidence interval. And what the confidence interval says is that there's a probability that some value is between these two items, or that it's in the confidence interval. And the more and more and more you test it, and the more and more the results seem to suggest that that's the answer, then you create what's called a theory after tons and tons and tons of testing. But the idea is that as soon as somebody else comes in with evidence that it's not true, or evidence that it's not the whole picture, then science will pivot on a dime to say, here's a better hypothesis that does a better job of explaining all of the criteria that we're looking at. And so what's kind of interesting about this is we're never proving something true, we're just proving that we think it's true, and the more and more evidence that suggests it's true, we tend to think, okay, this is probably what's true. But the minute somebody comes in with new evidence, we have to reevaluate everything. And that has happened several times over the course of history. And that's why science and the scientific method is such a great way of determining fact. Anyway, I'm sorry, I'll get off of my rants now about science, but let's look at this question. A data set includes 103 body temperatures of healthy adult humans having a mean of 98.9 degrees Fahrenheit and a standard deviation of 0.65 degrees Fahrenheit. Construct a 99% confidence interval that the mean body temperature of all healthy humans. What does the sample suggest about 98.6 as the mean body temperature? Excuse me. So if you're a health student, you probably know that 98.6 is regarded as the average temperature for a healthy human body. And so we took a sample. We were questioning this. That's a theory. So let's question it. We took our own sample and we found that it was 98.9. So which one's right? Are we right, or is the community right? Well, let's find out. So we're going to make our confidence interval. Notice that we do not know the standard deviation of the population. We only know the standard deviation from our sample. So that means we're going to be using the t-statistic formula. So let's write down all the values we need to know. First, we need to know x bar. So x bar is going to be equal to 98.9, which was the value we got from our survey. S is equal to 0.65. We also know n, which is 103. And remember that we also need to know degrees of freedom, since we're going to be doing a t statistic. So degrees of freedom in this case is 1 minus n, so that's 102. And now let's find our t alpha over 2. Okay, so we're going to find our t alpha over 2. 99% confidence, and we're doing two-tail because we're doing a confidence interval. So we come over to our t-table, and we scroll down. So two-tail confidence level, 99% two-tail, and we have about 100 subjects, and so that's 2.626. So again, all confidence intervals are two-tail. Two-tail, 99%. The closest number is 100 for our 100 for our degrees of freedom. And so we have 2.626. So I come back to my notes, and we're going to write 2.626. Those are all of the values we need to do our confidence interval. So let's construct it. For those of you following along, I'm doing this formula right here, with the T and the S, for our unknown survey. This is the formula that's used more in real life because we don't know the population parameters. So, confidence interval would be X bar 98.9 minus our critical value 2.626 times S, which is 0.65, divided by the square root of n. And remember, we do n here, not degrees of freedom, so it needs to be 103 here, not 102. That's going to be less than the population mean, less than 98.9 plus all the rest of this, 2.626 times 0.65 divided by the square root of n, which is 103. So we only use degrees of freedom to get the t-test statistic. Okie dokie, let's grab our calculator. So that's 98.9 minus 2.626 times 0.65 divided by the square root of 103. And we get 98.73. Yep, and that's the correct answer. They rounded it on this problem to 3 decimal places, so I'm going to write 98.732 is less than U is less than. Come up here, grab what I wrote, hit second and then left to move all the way to the left, and then I can just trade out my minus for a plus, and we'll get the right-hand side, which is 99.068, which is also correct. There's your confidence interval. So hopefully after seeing a couple examples, it's starting to make sense. What does this suggest about the use of 98.6 as the mean body temperature? Okay, so that's the question that they're asking. So you'll notice that where is 98.6 in here? Notice that 98.6 is lower than the low end of our confidence interval. So if you're a scientist and you do a study and you find out something like this, that can be really surprising, really shocking, because you're saying, wait, hang on a second, maybe this 98.6 isn't true. Maybe science has missed something, or something has changed. Like maybe climate change is causing people's temperature to rise, or maybe the population is becoming less healthy on average, and so 98.6 maybe is not the right answer anymore. So what this does is it suggests that the true mean body temperature of the entire population could potentially be higher than 98.6 because our entire confidence interval was above 98.6. So that's one explanation, and we were pretty high confidence, 99%, so that's pretty high confidence that 98.6 is not included in this. However, there's two things to note about this. Number one is if you publish a study like this, what other people do is they do their own studies and to see if they can replicate your study. And there's one important critical thing to remember about this. Remember that we only have a 99% confidence level. That means that there's a 1% chance that this confidence interval is totally wrong, even if our sample of 103 was a random sample. And that's because it's a random sample. You might just get unhealthy people or people who are sick into your sample, or a couple people. You don't even need everybody to be sick. If a larger proportion of sick people are in your sample than on average the average population, then that's going to be enough to affect your results. So other people will then do their own study, maybe with a bigger sample, to see if they can match your result. And if they say no, 98.6 is actually the correct answer, then what that means is your study would be called an outlier. It's not that you did anything wrong, it's that it's just a mathematical outlier. Maybe you hit that 1% that you just had an unlucky sample. Or maybe your 103 people weren't representative of the true population. Or maybe everybody drank coffee that day and right before getting their temperature taken, and they all had a slightly higher temperature. There's a million things that can mess up your data, and that's why we're not proving anything with this study. This study would cause other studies to be made, and then over time we get an idea of what the actual true answer is, and the answer might change over time, might get hotter, but anyway, that's the idea of science. That's the idea of doing these studies. So anyway, so I'll leave it at that. Hopefully this example makes sense, and if you have any questions, please contact me. We'll do one more example, answer a couple quick questions, and then I think we will be done with Chapter 7.